Okay, so in the last lesson, we looked at different ways that we could count numbers of outcomes, and we used some basic ideas. One way that we could look at all of the possible outcomes for a sample space was to use a tree diagram and actually see and be able to list what all of the possible outcomes are. We also used the fundamental counting principle, which allowed us to take objects that were disjoint, that had no outcomes in common, and we could find the number of different possible outcomes just by multiplying the number of ways that each of those disjoint or mutually exclusive things could happen. Today we're going to look at some complicated ways of counting numbers of possible outcomes. We're going to be talking about permutations and combinations. So an arrangement of things in a certain order is called a permutation. So in a permutation, the big thing to remember is the order that we put things is important. The number of permutations of n objects taken r at a time, we denote using this symbol p of n and r, or we can call it npr. The calculation for a permutation depends on if the objects are distinguishable, meaning we could tell the difference between each of the individual objects that we're arranging. So if all of the objects are clearly distinguishable, then changing even one of those objects in the permutation leads to a different permutation. So the idea behind a permutation is we can have the same objects within the group, but the order that the objects are in matters. So having A and then B would be a completely different outcome than having B and then A. So the number of permutations of n distinguishable objects taken r at a time. So we have n distinguishable objects, and we're going to put r of those objects in a certain order. We can find that by using this formula where our permutation of n objects taken r at a time is equal to, and this little exclamation point means factorial. When we're looking at a factorial, we're multiplying the number times every consecutive integer that's less than that number all the way down to 1. So when we're looking at n factorial, really what we're saying is n times n minus 1 times n minus 2, and so on down to 3 times 2 times 1. That's what that factorial means. So to find the distinct ways that we can order n different distinguishable objects taken r at a time, we would take n factorial and we would divide it by n minus 1 factorial. And again, that's only if we can distinguish between each of the objects that we're arranging. If, however, not all of the objects are distinguishable, then we must take that fact into account when we're counting our permutations. So for example, if p of the objects are indistinguishable and another q of the objects are also indistinguishable, then the number of distinguishable permutation of n objects is going to be n factorial divided by p factorial times q factorial. And we can extend this to more than 2 objects. So if we had another group of indistinguishable objects, we would take how many of those indistinguishable objects we have and multiply it times its factorial. So in this first example, they want to know how many ways can we place 3 books on a shelf if they are chosen from a selection of 8 different books. So we have 8 different books, 8 distinguishable books, and we're going to select any 3 of those 8 books to place on a shelf. Now, since we're looking at the way that they can be arranged, we could have the same 3 books arranged in different ways, and those would count as different arrangements. So the order that we place the 3 books that we select on the shelf matters. That means that we are looking at a permutation. So we are doing a permutation. We are looking at 8 objects, 8 distinguishable objects, and we are going to pick 3 of those 8 objects. And we want to know, again, how many different ways could we arrange those 3 out of 8 objects. Well, according to our formula, that would be 8 factorial divided by 8 minus 3 factorial. or 8 factorial divided by 5 factorial if we simplify. So again, when we're looking at the factorial of a number, we're taking that integer and we're multiplying it by each consecutive integer less than that number all the way to 1. So for example, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So then we're going to divide that by 5 factorial, which is 5 times 4 times 3 times 2 times 1. Now I could go ahead and multiply the top out and multiply the bottom out, but since these have common factors, it's going to be a whole lot easier if I go ahead and cancel out the common factors. So for example, I have a factor of 5 in both the denominator and the numerator. I can cancel that out. Same with the 4s, the 3s, the 2s, and the 1s, although the 1s really aren't going to make a difference in our final answer. So once I simplify that, I see that really all I have is 8 times 7 times 6, which would give me 336. So if we have 8 books to choose from, 8 different books to choose from, there are 336 different arrangements that we could make if we chose 3 of those books, any 3 of those books at a time. The next example wants to know how many ways we can take the letters from the word Georgetown and arrange them. So again, a big key here is that word arrangements. Anytime you see the word arrangements, we're saying that different orders would count as different sets. So that makes this a permutation. However, in this example, notice that not all of the items, in this case the letters, that we're arranging are distinguishable. For example, the letter G. I have 2 G's in the word. If I were to take those 2 G's and switch them around, I would get the exact same arrangement. So the idea here is that I've got 2 of these items, the G's, that are indistinguishable. So I have 2 G's that are indistinguishable, which means I'm going to need to alter my formula a little bit. And the G isn't the only thing that's indistinguishable. We also have 2 E's. If we were to take those E's and switch those E's, again, we would have the exact same arrangement because they're indistinguishable. So we need to take that into account in our formula. We have 2 E's. We also have 2 O's. So we have 2 G's that are indistinguishable, 2 E's that are indistinguishable, and 2 O's that are indistinguishable. And so to find the number of different arrangements for those letters, we're going to use that modified formula for the permutations. N is the total number of items that we're arranging. In this case, that would be the numbers or the letters in our word, Georgetown. So we have 10 different letters in the word Georgetown. So we're going to have 10 factorial. And of those 10 different items, 3 of the items have values that repeat. So we have 2 G's that are indistinguishable, which means I need to divide that by 2 factorial. We have 2 E's that are indistinguishable, so I need to divide that by another 2 factorial. And we have 2 O's that are indistinguishable, so I'm going to divide that by another 2 factorial. The idea is that we're dividing out the replications so that we're not counting them twice. Again, if I switch the G's or switch the E's or switch the O's, I get the exact same arrangement of letters. So what I'm doing is dividing out those repetitions. All right, so I have 10 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Over 2 factorial, so 2 times 1, times another 2 factorial, 2 times 1, times the third 2 factorial, 2 times 1. And I can go ahead and cancel a 1 and a 2 for both the numerator and denominator. Really, these 1s here I could leave out if I want to as well. So if I multiply all of that out, the numerator and denominator, and divide it, I'm going to end up with 453,600. In other words, there are 453,600 different ways, different distinguishable ways that we could take the letters in Georgetown and rearrange them. So in some cases, we want to consider the order, and that's true in both of those examples. But in some situations, the order that we take things might not matter. So a combination is a selection of objects where the order is not important. The number of combinations, n, taken r at a time, is denoted using the symbol C of n and r, or NCR. Since the order is not important, we alter our formula a little bit to eliminate duplicate combinations. The idea behind a combination is we're looking at taking r objects from a group of n things, and we don't care what order. So in a combination, A times B, or having A as our first selection and B as our second selection, is the exact same thing as getting B in A. A lot of times when we're just looking at different groups of objects, we're talking about a combination, because it doesn't matter if you're picked first for the group or if you're picked last for the group, you're in the group. So the order that those things are selected doesn't matter in a combination. So to find a combination of r items taken from a group of n, we take our permutation formula and we alter it a little bit. We have n factorial divided by n minus r factorial times r factorial. So we have that extra added factor of r factorial. And what that's doing is it's counting out the replications where the order is insignificant. So in this next example, it says that from a group of 10 men and 10 women, how many committees of 5 men and 6 women can be formed? So again, we're talking about groups. We have 10 men. We're going to choose 5 of those men to be on the committee. It doesn't matter what order those men are selected. So whether you're the first man selected for the committee or the 5th man selected for the committee, you're going to be on the committee. The same for the women, except we're going to select 6 of the women to be on the committee. So I'm going to start with how many different groups of 5 men I could choose from that group of 10 men. So looking at the men, I have 10 men. I'm going to select 5 for my committee. So for the men, I'm having a combination. I'm going to choose from 10 items 5 to be in the group. So from 10 men, I'm choosing 5, which means I have 10 factorial divided by 10 minus 5 factorial times 5 factorial. So I have 10 factorial divided by 10 minus 5 is 5 factorial times 5 factorial. So that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 5 factorial, so 5 times 4 times 3 times 2 times 1, times another 5 factorial, 5 times 4 times 3 times 2 times 1. And now, just to make this easier to evaluate, I'm going to cancel out the common factors. So I've got 5, 4, 3, 2, and 1 that I can reduce by. So my numerator, I've got 10 times 9 times 8 times 7 times 6, which is going to give me 30,240. Divided by my denominator, I have 5 times 4 times 3 times 2 times 1. Gives me 120. So if I divide that out, I get 252. So in other words, there are 252 different groups of those 5 men that I could choose from a group of 10 men. Now I'm going to do the same thing with the women, except that for my group of women, I'm choosing from the same size group, 10, but I'm going to choose 6 women instead of 5. So we have 10 women, we're going to choose 6 this time, which means that we have 10 factorial divided by 10 minus 6 factorial times 6 factorial, or 10 factorial over 4 factorial times 6 factorial. So I have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So again, I'm going to start by making this smaller by canceling out my common factors. So my numerator, I have 10 times 9 times 8 times 7, which gives me 5,040. In my denominator, I have 4 times 3 times 2 times 1, which gives me 24. And so if I divide that out, I get 210. So there are 210 different ways that I could choose 6 women to be on this committee out of 10 women. Now, we're not quite finished yet because they want to know how many different committees of 5 men and 6 women. So now we know how many different ways we could choose the men. We have 252 ways that we could choose the men for the committee. And we know how many different ways we could choose the women. We have 210 different ways that we could choose the women on this committee. They want to know how many different ways we could choose both of those collectively. And these groups would be disjoint. You're either going to be chosen in that 10 group of men, or you're going to be chosen from that 10 group of women, but you're not going to fall in both of those groups. So since these events are disjoint or mutually exclusive, if we want to know how many different ways we could have one or the other, then we can use that fundamental counting principle that we learned before. So the number of ways that we could choose from 252 men or 210 women is just going to be the product of those two. So there are 52,920 different committees that we could select, choosing 5 of those 10 men and 6 of those 10 women. So there are some shortcuts that you can use to evaluate some of these. You can type a factorial into your calculator. We also have commands for permutations and combinations on our calculator. So permutations and combinations can be evaluated using your TI-84 calculator. If you press the map and you go to your probability menu, this is the menu where we used option 5 for our random number generator. Notice options 2, 3, and 4. Your command for your permutations, is going to be your command for your combination, and if you just want to type in a factorial, that's going to be option 4. So I want to go back over these examples real quick and would evaluate them using a calculator. If we were doing this first example where we were doing a permutation of 8 objects taken 3 at a time, first you need to type in the number of objects you're selecting from. So in this case, we're selecting from 8 objects. Then you're going to choose your permutation command, so you'll do map probability, and you'll select option 2. And then you're going to type in your R value, the number of objects you're selecting. So we're going to select 3. So we have 8 objects. We're choosing 3 for our permutation. And if we press enter, we get the same thing that we calculated earlier, 336. If we look at that last example, we were doing combinations. So for example, I'm just going to do the men here. We had 10 men and we were going to choose 5 for our group. So again, we start by typing in the number that we're selecting from N, which would be 10. Go to our math menu and pull up probability. This time we're doing combinations, so we'll select option 3. And if we chose 5 of those men, we get that there are 252 different combinations we can create. For our women, we chose 6. There are 210 different combinations of 6 women that we could choose from our group of 10. And finally, if we have something like our permutations that have objects that are indistinguishable, we can still evaluate that using our factorial key without having to go through all of this process of writing out and simplifying each factor. So for that middle example, the letters from Georgetown, I could type that in as a fraction if I wanted to. On top, I have 10 factorial, so I type in 10, and then I go to my probability menu. And this time I'm just choosing the factorial, which is option number 4. Oh, kind of hard to see there. There we go. Then in my denominator, I have 2 factorial times another 2 factorial times a third 2 factorial. So I have 10 factorial divided by 2 factorial times 2 factorial times 2 factorial. And we get the exact same number of arrangements there, 453,600 different ways that we could arrange those letters. So I wanted to make sure that you guys understand the process of what factorials mean and how they work and how we can simplify them. But if all you need to do is calculate permutations or combinations, you can also evaluate those very quickly using your calculator.